So I'm gonna continue from where we stopped last time. So the topics that I'm going to cover for today is, as you can see over there, is graph neural net or graph convolutional networks. So since we have graph in the name in the network, so I kind of spent some time to explain what the graph is last time, and just like like a convolutional neural net. So if you remember it, the CNN is convolutional neural net, and so at that time I spent some time to explain what the convolutional operator is. So I guess at this moment you kind of get some ideas or what the graph is. So think about what kind of key ingredient or components to make the graph, and why we want to do graph, like represent some kind of relationships and connections, connectivities, things like that. And there are some another definitions under the graph, like the first one is degree and what's the adjacent matrix, things like that. So graph is like, we can on that side it's like that's the kind of one way that we can visualize it, like is easily to understand. But thing is that we have to make computer to understand. One of them is ways that using the adjacent matrix. And this is kind of the motivations for that, is that for supervised learnings, like from the raw data, we try to extract the features. So this could be the features, and we assume that all the data points, featured data points, are independent to each other. So that's the key things. And sometimes it's going to be useful if you take the connectivities or dependencies into the considerations. One way that we can instead have that they represent the kind of dependent relationship into the graph. So there will be each node have associated or corresponding features. So that was the motivations. And again, this is another slide to show you the adjacent matrix. I think I have some animations that you can see. And there are similarities between CNN and GCN. GCN is graph convolutional networks, or so graph neural net and graph convolutional neural nets are different, but in this course I'm going to use GCN and GNN are pretty much the same. So the major difference for CNN is that all the data is just in structured, regular structures. So you can think of as a grid, or in pixels in the images. So we define corners and we do convolutional operations over the images. The biggest difference is that the graph on this side is not regularly structured. And number of nodes connections vary, and nodes are unordered, and those are the key characteristics compared to regular structured data. For example, it's images. Now let's start talking about basics of GCN or GNNs. And let's see, for example, here. So I want to update it. So here is message is the same. So again, in here I'm going to explain what the message aggregation update. But before that, let's see this one first. And here in graph neural net, they use a term message, but you can think as a features. So there's some features associated this node, and another features or message in the node, h of 1 and h of 2, things like that. And I want to update it this guy. But we know that the prior knowledge that we have is that this guy had a relationships or connectivities with these two, not this guy. Okay. So this will have some, let's see. Unlike CNNs, each node of GCN has a different number of adjacent nodes. So this guy has different adjacencies and this guy has different adjacencies. Also, in those, the informations are located and can be found in the adjacent matrix A. Okay. So there are three key steps, key components. The first one is message. You can, again, it's I would say, pretty much same as features. So some of the information is passed by the neighborhood node to the central node. So to update this guy, to update the message on this guy, and we have to look for what's the neighborhood. So in this case, 1 and 4 are the only neighborhood. So I want to take some information from those, to use that information to update this guy. I don't need anything from this guy because it's not connected. It's connected in this way, but not directly connected. And in the updating process, we kind of split two steps. The first step was the aggregations or aggregate. So we aggregate first, then we update it based on the aggregated informations. So collect information from neighboring node. Right? Then next step is gonna update it. So I kind of, in order to visually represent the updating, so this one is kind of visually updating aggregations. And I kind of, to show that this guy is updated, so I use a different colors. Right? Two steps. Aggregations and updating. Those are the key process. At this moment, don't worry about how to aggregate, don't worry about how to update it, don't worry about it. We're going to go through that process. But conceptually, so we define the graph first in order to represent demonstrate the connectivities or relationships. In graph, we can draw the graph, and we can get adjacent matrix. So we have those informations. And for each node, we define the message or so feature factors. Then each iterations, we're gonna update it. How? Aggregate first. Then next, followed by the updatings. So let's see in details. Again, we don't know how to aggregate yet, but in this one, let me see. I guess there's some typos. This one is V. So again, this is iterative method. So in kth iterations, we do have some updated messages like that. And V, this one is U. I'm kind of confused, U or V. So I want to update it node U, and this one represent the neighborhood. All the node belong to neighborhood of U, right? We have to consider those the messages. And we have to aggregate somehow. We don't know how to aggregate yet. So that's how we update it. And this one is kind of the matrix representation. And so A is adjacent matrix. So let's take this one as examples. And in this case, this is associated adjacent matrix. Let's see. The first node had all the connections. That's why we have 0, 1, 1, 1. And this guy connected to the 1 and no connection. And this guy 1 and 4. That's why we have 1 and 4 and zeros for others. And for this guy 1 and 3. So 1 and 3. Right? And we have 4 nodes, and these they are the messages at the current at kth iterations. So we have h of 1 and h of 2, and these are the transposed column vector, right? And if you do this multiplication, these are the adjacent matrix, and this will be the matrix. And if you do matrix multiplication like this guy, let's see how. We're gonna do like that. We're gonna do matrix multiplications. Another way that we can write it, this guy. Let's see. We're gonna do this, and what I'm saying is that plus this will be guy, this one. Let me see, right? That means here aggregation is the simplest one is do the summations, the vector summations. So for updated, so I want to do aggregations for this guy. How to do? Just take the connected messages, h of 2 and h of 3 and h of 4, and do summations. This will be updated one. So there are many ways that we can do aggregations, but the easiest one probably like add, like additions. And connectivity information, we can get it from the adjacent matrix, things like that. And just matrix multiplication, that's it. And for this guy, for example, like we're gonna do this. So h of 1 plus 0 h of 2 plus 1 h of 3 plus 0 for h and 4. So only gonna take the first and third, which is first and third. Right? Now, next step is once we're done with the aggregations, we have to update it based on the aggregated messages. So how? So you have to see the I'm gonna erase it. So you have to see. So this is just aggregation process. So I update it. You see, So I want done with the aggregations, we have to update it, and the difference is that we have another matrix multiplication, omegas and sigmoid functions. So again, there are many ways that we can do update, but again, it's the simplest is that like we just introduce another matrix to the matrix multiplications, but for matrix multiplication, only thing that we can do is linear transformations, and we need to inject nonlinear like functions. That's why here the easiest one is sigmoid. Any kind of nonlinear activation functions that we learn in deep learning, we can introduce. So these aggregated messages, right? And we have omega matrix. Have all the elements here. So these omegas, and we'll do another matrix multiplications, and we'll get updated one. But these are only linear combination of this guy. So that's why we put it into the sigmoid functions. Then we have the dimension or shape is going to be the same. But these updated values, the elements going to be linear combinations and followed by the nonlinear functions. So that's why we are able to do nonlinear activations as well. And don't worry about what kind of values inside the omegas. Don't worry about it. Some random numbers. We can define it, but I think the idea is that later on we're gonna ask deep learning models to find out or figure it out based on the training data set. Right? These are gonna be some trainable parameters inside. So this guy at the end would do aggregations and update. Update is actually there are two linear combinations followed by the nonlinear activations. We call it update. So we will get this guy. Again, starting from the same size. So each message is updated one. So that's why I said I just had different colors to show that this one is updated. That's one iteration. And we're going to do another iteration. So these are the messages associated each node. Going to keep updating. It's like if you think about the GNNs, we have the first convolution layers and followed by another convolution layers. In the graph, we're going to do aggregations and update. That's the kind of one basic block. We're going to do consecutive updates. So that's kind of the basic idea of GCN or GNN. But that's not the end. We have to think about the further improvement. There are the drawbacks in these guys. So actually, that's why I blocked something. So we have to do further improvement. What kind of further improvement is that? The message passing with a self loop. Remember, in this case, in order to do aggregations to update this guy, we kind of refer to the information or message from a neighborhood. But let me show you. I'm going to skip. So the first improvement that we can make is that here's no self loop. We add self loop. So having that, we add self loop each node. That means, see, in order to update this guy, we're going to take this neighborhood, including itself. to update, to aggregate. You see what I mean? No? That's why I remember in where is it? You guys remember? I'm going to. So let's see. So I want to do message passing with self loops. I want to include self loop. So as it's a common to add self loop to the input graph, and that's why I see. So I want to update it with aggregated neighborhood and itself. Because I want to include, I want to update it based on the myself and my neighborhood, which is, I think it makes sense. So in order to represent that case, I want to update it based on myself and aggregations. And pretty much I can do same things, update it, aggregate it, but when you do aggregate it, this is my definition of neighborhood and myself. And these are the same representation. Here, with aggregate, I want to aggregate it based on my neighborhood first and include myself. But here, when you do aggregate it, neighborhood and include myself. I mean same. In matrix representation, here that's what I used to do it, and I want to use A plus identity matrix instead of A. You see what I'm doing it? By add identity matrix, that means I include self loop into adjacent matrix or into my graph. So I made small improvement. And another issue or second improvement that we have is again normalization issues. The simplest or the most basic neighborhood aggregation operation is simply take the sum of neighborhood embedding. That's what we did so far. But one of the issues when you compute it or when you update it, it's going to be unstable and highly sensitive to the node degrees. Some node has many edges, some of them don't. So in order to kind of remove these kind of issues, avoid these kind of issues, another solution that we can think of is, where is it? We simply normalize the aggregation. And I kind of show that how to normalize it. Remember? And one way that this is kind of normalized, but again, this is not, because although these are the undirected graph, in this one's is not symmetric, that matrix. So we use this kind of computations. Okay, so I'm not going to use A matrix. I'm going to use A plus I, because I want to include self loop as well into my considerations. And another thing is that, again, I'm not going to use this guy. Instead, I'm going to use this, which is normalized. Those are two improvements that we can make. So this will be the kind of finer things that we can have. So let me say that again. So this one was the the original thought. We do aggregations, and we do update. Now I want to add self-proof. See this part without self-proof, and I decide to include self-loop. And the difference is that here I use A plus I instead of A. Others are pretty much the same. Okay. See, A and A plus I. Now I want to normalize it. So this one was A plus I, and I'm going to use A tilde. And these are the A tilde matrix. So those are the finer things. Okay. So let's think about the aggregations and update for a moment. And given graph, so suppose the graph is given, then we can get A matrix, which is adjacent matrix. We can compute A plus I, and we can compute A tilde matrix. It's automatic. So these will be the given. And H's are the feature vectors of messages. So there's no control on that. And the sigma is sigma, and any kind of, we can use a LELUs or sigmas, whatever. It will be the nonlinear activation functions is going to be given as well. I mean, once we decided, there's no. So the thing is that the omegas. This is it's a kind of, when you talk about the convolutional neural net, this is kind of the corner. So if we have different omegas, we will get different updates, right? So omega is the only Okay, so the question is, which one is, so in these, the aggregations and the update process, which one is trainable? Which one is trainable? In CNN, which one is trainable? Kernels, right? The omegas you remember, like 3-byte kernels, or the elements. In convolutions, starting from the convolutions, in the specific kernel is going to make specific effect onto the image. Right? And same here, if you define some omegas, it's going to make some specific effect when you updated the messages. But we're going to do opposite directions. We do have input and output. And this is, we want graph neural net or deep learning models trying to figure it out. This is the omegas based on the training process, iterative way. You see what I'm trying to do? So the omega is the only trainable parameters. You can think of it's like just like the kernels in CNN. Remember, in CNN we learned kernels from the data. We're going to ask the CNN models to find out the proper kernels, right? That's why we do kernel design. So it's same thing in GCN models as well. So omega is the only trainable parameters, and instead of me putting some specific numbers inside the key elements on the omegas, say I have no idea, but I do have data and training data set. I want to find out. I want to ask the deep learning models to find out for me. That's the kind of fundamental philosophy. Okay? So omega is the only trainable parameters. So this is going to be final. Finally, we can have finalized the graph convolutional neural networks. In the mathematical expressions, we have, again, the H is we stacked messages for each node and self-looped and updated omegas and sigmas. But this is better because we do neighboring normalizations. And the only difference is that A plus I, we have instead of that, we use A tilde, which is normalized. So let's see what's going to happen inside. So suppose we have this kind of graph is given, right? And see, in CNN we have multi-convolutional layers. So in GCN we have multi-layers as well. So in the first layer, let's pick. So we're going to update all the nodes inside the graph. For instance, for this guy, we know that these are the neighborhood. So based on these aggregation, of course we have self-loop, but we didn't the indicator here. But assume that is including the self-loop, and we do neighborhood normalization as well. So based on these, we update it. And for this guy, based on these neighborhood, we update. That's what's happening in the first hidden layer. And followed by any kind of nonlinear activation function. It could be Lelus, it could be sigmoid, it could be tangent hyperbolic, whatever. And if you have another hidden layers in GCN and graph convolution neural nets, right? Now we did the updated one. Based on, so this one will be the inputs and this will be the outputs. So again, I'm going to update this guy based on these, but these are not the same as the message or the feature vectors. These are different from because we kind of had updated. So we will repeat this process based on the updated messages as well. Okay. So let's see so suppose we have only two hidden layers. Then to update this guy, we utilize these. But this one is updated. So for this guy is in the previous hidden layers updated. Okay, so what I'm trying to say is that I want to show you this one. So suppose we have only two hidden layers. So I have A, and first we update B based on the B, C, and D. But B, C, and D is the updated one in the previous layer. So B has from A and C, and C is from AB. C is from A, B, E, F. A is from D is from A. That means if you have two hidden layers, for instance, for A, I'm going to these are my neighborhood, but for how do I say? So it's kind of the first jump. And if we do have two hidden layers, that means I will do up to second jump. You see what I'm trying to say? So the F is kind of indirectly connected to, so to update A, if we have two hidden layers, that means in the first hidden layers, in order to update C, I'm going to use the information from F as well. So this information is going to pass to C, and based on the updated one, I'm going to update it A as well. So if you add, that means add more hidden layers, that means I'm going to consider more and more neighborhoods into consideration. So that's, I think the explanation is not clear. So let me. So for D, if you have only one hidden layer, I'm going to take the information from A. That's it, right? But if you have two hidden layers, since A is updated from B and C as well, so in first hidden layers, A is going to update it from B, C, D. And we have followed by another hidden layers. So D is going to take the updated, going to make updations based on the A. So these informations going to make some kind of effect onto D. If you add another layers, C is updated F, E, and F as well. So that means in order to update D, we take the informations or messages or features from the entire graph. Okay, that's kind of, the basic stuff. I think I done with the explanations, and at least I hope that you got some ideas. So my recommendation is that for GCN and CN, always trying to think, this is the operations in GCNs, and think about what kind of related to the operations in CNN, things like that. So go back to how to implement it, in Python, and from graph we can get a matrix. This is, let's see H. This is adjacent matrix. And I want to define H is this is let me see, H. No, not this one. H is this way. So so this is H, right? So the example that I have here, what I'm trying to say, so I assigned, so in message is like H is like, and the simplest one is that this one's color, so it's 1D. So I assigned 1 and assigned 0 and assigned -1 and zeros. That's my message for each, associated each node. Okay? And AH is if you do this kind of multiplications, A is adjacent matrix. So this is what I got, but the way that you're supposed to interpret this guy is that for this one, I'm going to take the message from neighborhood. So I got from zeros and -1. That's why I got -1. And for the second node, I got the message from neighborhood 1 and zeros. That's why I got 1. Let's do this guy. The neighborhood from 0 and 1. Got 1. For this guy, let's see, 1, 0, 0. That's why I have 1. And for that guy, -1 and 0. For this guy, 0 and -1. You see what I'm doing it? So that's related to A times H. Now I decide to add self loop. So this is A plus I. Now remember this one was zeros. And now we add self loops. Let's see what we got. For this one, I got from my neighborhood 0, 0, -1. But I do have self loop and +1. That's why I got 0. Right? And let's pick this one. 1, 0, 0, -1. So I have 0 here. Now do normalize. This is a tilde. And we cannot calculate by hand. That's why I had this one. Now let's build up the GCN models. I use ReLUs as an activation function. And in omega, what I'm trying to do is that, remember, here omega is the only trainable parameters, right? So eventually what we're going to do from the data, we're going to ask the deep learning models to find out the omegas. But in order to see what kind of effect we can make out of omegas, the omega matrix or big W, I do randomly assigned omega and randomly assign it, right? To do fold propagations to see what kind of fold propagation that we can make it. So randomly assigned. Why we have W1 and W2? Because we have 2 hidden layers. So suppose we got some omegas. I mean the W matrix. And I want to show you how to do fold propagations to see. And we can put the numbers, but here I just do to randomly assign the values into W1 and W2. And non-linear functions here, ReLU, so we implement the ReLU functions. And the GCN, let's see, we compute D matrix. Let me see, D and use, and this is A tilde, and we do H and the omegas. That's how we aggregate and update it. And at the end, we put the ReLU as a nonlinear activation functions. That's going to be the output of GCN. Okay. So H is the first one, and put the H1 with W1, it will be the H2, the updated messages. And from updated one, we do have randomly assigned the W2 for the second hidden layers. That's we got H of H3. That's what we have here. I wanted to show you how to compute the 4 propagations. Assume that we have the W's. So this is the H. So remember, at the first time we assigned, what was the H1 was like this one was the H, right? Now, since if we have 4x2 matrix, we can change the length of methods as well. So in this case, this one is the message associated with the first one. So, like, we got updated. So the message the length can be changed. It really depends on how we define the W matrix. The last one. There's still the minor issues. Not the minor, the big issues. We do have big issues. The problem is that all 2 graphs has the same network structures. Adjacent matrix can be different. What does that mean? Let's see. This is a graph, and this is another graph. Do you think these 2 are the same or not? Look at the colors. Yellow and yellow, you think about the connectivities. And we know that from these 2 drawings, these 2 graphs are identical. And I'm going to put, let me see, some 3. Like 1, 2, 3, 4. And what about 1, 2, 3, 4? Is that right? 1 is connected 2, 3, 4. Yeah, and 3 is connected. 3 is connected 1. Yeah. If you do different numberings, adjacent matrix looks totally different. But we know that these two are the same. In a topological sense, they are the same. But somehow the computer's gonna think those two are different because you have different, looks like the adjacent matrix are different. So somehow we need to make permutation invariant. Somehow we have to tell the computer that these two are identical. How we do? We call it read out. Don't worry about the name. You don't need to know. And there are many ways that we can do. We can do permutation invariance. But again, the simplest way that we can do is that just do summations at the end. If we do summations at the end, if we do permutations inside, it doesn't matter. You see what I mean? Okay, so if we do A and B and B and C, I mean B and A are different but are the same, right? So if you're changing the sequence or the orders, we call it permutations. The summation if we have summation operations at the end, it is going to be permutation invariant. So again, you do graph and feature the H matrix and do summations. We call it read out. This is kind of very special operations because we have in the graph has this kind of the issues, topological issues. Topologically the same, but somehow if you do the adjacent matrix representations, computer might think these two are different. But here we do, if we add the summations, we can kind of solve the readout can solve the permutation issues. Right? So this is the final given graph. We do graph convolutions many ways, many times, and the readout, and do, if that's the classification problems, whatever, we can add some kind of sigmoid or softmax at the end. We do predictions. And you can think of just like images as an input and see convolution net, convolutions, and like fully connected layers at the end. Here, similar to GNN, we do multi-graph convolution layers. This one is, I already explained it. And if you add multi-graph convolutions, that means in order to update this guy, we consider many neighborhoods and like jump 1 or 2 jump and things like that. What kind of task that we can do for GCN or GNNs? People like talking about 3 major applications, and task 1, 2, and 3. The first one is that, say this is the graph that we have, and let me see, it's classification problems. We use different colors to represent different classification that for each node. And say these are like belongs to whatever green class, and this one is purple and red. And we don't know the colors for this node, whether it's green or yellows and purples. And we call it node classification problem. Node classification problems. If you formulated these kind of problems into graph, this guy, in order to decide what kind of class that gonna take the masses, features, plus the connectivities information as well. The second task, suppose we have this kind of graph, and we are not sure these two are connected or not. I want to see whether we have connections or we have connectivities or relationships, or we want to figure it out. So like we have edge prediction problems. Another task is that for the graph, here the difference that the first one is that I add labels into each node. Here I want to put labels to entire graph, entire network. So this one is like, say, like label A, and I'm not sure whether this is like another labels or this. Say this is label A and this is label B, and I suppose we have another network, and I want to see if it has more similarity on this guy or more similarity on this guy. So it's a graph classification problem. So those are of course, we might have more like other applications as well, but these are the major tasks related to GNN or GCN. Node classifications and graph classifications and edge predictions, whether we have edges between two nodes or not. All right? And of course, we're not gonna program like GCN from the scratch. There are a lot of modules and libraries as well. There are many. And each library has pros and cons, and somehow, in this course, I decided to use a spectra. So we use these ones to demonstrate. So let's think about the examples that I want to demonstrate here. So I want to do node classification. I want to show the node classification problems as an example of GCN. The problem that we have, the example that we have is that there's some, this is the data set that we have. And what kind of problem is that? So in this scientific public and papers, right, I want to categorize like into 7 classes. See, so say I do have this amount of the publications and papers, journal papers, and these are related to, or we can categorize into case-based, and another is a genetic algorithm and neural nets and probabilistic reinforcement, whatever. So these are, we do have 7 classes. 7 categories, and these in the training data set, we'd have this amount of papers. I guess someone will read that and decide, hey, this paper is probably, we can classify it or we can label it as related to reinforcement learnings. And these. So in graph, we do have how many nodes will we have? How many? So node represent each paper. And we do have, okay? Now we have to connected. How? If we have, say, this paper had the citation on this, that means connected. Because each paper is going to have references, right? So then if we have the reference, we believe that these two are connected. So like say like that, like things like that. The next question is how we define the messages or feature vectors for this guy. So the way they did is that in that paper they have, from the dictionaries, if they have corresponding word inside the papers, we assign, what I'm saying is that, say, how many, so 100, right? Say the first, I'm not sure what kind of, like say, machine learnings. And what else? Maybe graph. So say this is the first keyword. If in this paper has this word inside, that means I assign it 1. If this, for example, does not have a graph word in, then I assign zeros. It's like one-hot encodings. For how many? This amount. So think about this, the length of the message. That's how we define it. So in summary, we have 7 classes, and this is the length of features or messages. We have almost 1,400, like things like that. And these are the number of papers and number of nodes. And remember the H shape. The H matrix is H of 1, H of 2, and H of, and each H, that's the size of H matrix. And if you plot it, this is the, for training data set, we use a different 7 colors to represent. And that's the connectivities, connected graph. How to implement it? Let me see, we create the graph and get it the adjacent matrix A, and add identity matrix to get A self. And this is normalized A tilde we have, and H is like given. So how do you GCN? Just don't worry about anything. Like say, remember in CNN we have TF dot layers, TF dot keras labels, keras dot labels dot CNN, right? Conv, right? And the only difference is that you use a scepter and layers and graph conv. And graph conv. That's the only thing that you need. Don't worry about anything else. What's inside? You don't need to worry about anything. So that's the only. So this is, if you decide to just to programming or implementing without knowing anything, without knowing what's inside or what's happening inside, still it's possible. You can do. You can build up the graph, the GCN models. But what's happening inside, I kind of explained it here. And compile it and summarize it and model.fit. That's the only thing that we do. So once in this process, we're gonna get W matrix, right? You're gonna get W matrix. So once we're done with train process, now we have new data set, then evaluate it. So see that paper's gonna make predictions, what kind of class, based on the words inside that papers. We kind of trying to figure it out, what kind of categories here. I mean, the difference is that the ANN or CNNs, we make classifications only based on this. Not based on this feature, messages, right? But the only difference is that since we have connectivities between papers, the reference, we utilize that connectivity information as well. How you implement it, you can think of GCN. And actually, implementation is not that difficult, because as you can see over there. Right, that's kind of all the materials that I prepared and that I have for related to graph and graph neural net. And I'm not sure whether you guys, in the process of your research, you might have graph related applications or not, but I decided to add the graph neural net in this course as well, because I think it's a typical ANN and CNN, but the graph is we can consider the connectivity informations, and those I think it's going to be the I hope that it's useful tool for your own research in the near future. And of course, all the explanations and materials are extremely simplified. So for the advanced learners, probably you guys can refer these, the reference, and the lectures and other. We do have the textbook as well, right?